So like I said, this section 5.1, there's two parts to it. The first part is called special, well, the whole section is called special segments and triangles. So the first part we define, there's 4 different segments that we talk about that you can have in a triangle. One of them we've talked about before. So mostly what we use, there are some theorems in this section too. The theorems that I'm going to go over, I'm not going to spend a lot of time going over them because we don't really use the theorems a ton. They may come up like here and there, but it's mostly the definitions of the 4 main special segments that we're going to use. So the first one is called a perpendicular bisector. So you can probably figure out what this is because we know what perpendicular means, right? Perpendicular is lines that form right angles. And a bisector cuts in half. So basically a perpendicular bisector is a line, a segment, or a ray that passes through the midpoint of a side of a triangle and is perpendicular to that same side. So if we have this triangle here, and the directions say create XY, the perpendicular bisector of AB. So it's going to be perpendicular to AB and it's going to be it's going to cut it in half. So what we're going to do is we're going to find the midpoint of AB. So this is where the ruler comes in. So AB is like about 5.5. So I would say about here, about 2.75. The midpoint. And then to make a 90-degree angle, you just set it up. So in case you haven't ever used a protractor, protractors will always have like something here, like sometimes it's a hole, sometimes it's like a little dot. Mine, it's just like a vertical line and a horizontal line. See how those like form a right angle. So that point here needs to go on the midpoint that I just made. And then this bottom line has to line up with AB. So you would set it up like this. And I can show you guys again next week. Next week is where you're really going to have to know how to do this, like use a protractor and stuff, but I'll remind you next week. And then so this, I marked at 90 degrees. I'm just going to connect this to this. And it said line XY, so I can just make it a line. So then I need to just label it with an X, and I guess I'll make this Y with arrows. And so XY is a perpendicular bisector because I just made it 90 degrees, intersected at 90 degrees, and I made these 2 pieces equal. So how we would use this is you would be told that there's a perpendicular bisector. And so you could mark and say that AY is congruent to YB, and then also that this is a right angle. And so is this, both sides are right angles. So that's a perpendicular bisector. You can have 3 perpendicular bisectors in every triangle. Every side can have a perpendicular bisector. So I could draw one through here. I could draw one through here. Now, when you have all 3 of them drawn in, they all intersect at one point. That's called the point of concurrency. That's the second part of this section. That's what we're going to do on Thursday. So real quick, I'm just going to go over these 2 theorems, but like I said, we don't really use these theorems a ton, but I'll still talk about them. So there's the perpendicular bisector theorem that says if a point is on the perpendicular bisector of a segment, it's equidistant to the endpoints of the segment. So let me zoom in a little bit here. See AB here. DF rather, or DE, whatever, is the perpendicular bisector of AB. So that means that any point on DF would be equidistant to A and B. So here's the examples they gave. So D is equidistant to A and B. Equidistant just means same distance. So like those 2 would be congruent. E is also equidistant to A and B. So these 2 would be congruent. F is also equidistant. So these 2 would be congruent. So going back to our picture here, any point on here, so this X, if I wanted to connect it to A and B, those would be congruent. So it comes up sometimes, but not really that much. And then there's the converse. Remember what a converse is? A converse is you take a theorem and you flip the if and the then. So the converse of the perpendicular bisector theorem would be if a point is equidistant to the endpoints of a segment. So see how they marked AD is congruent to DB. They marked AE congruent to EB, AF congruent to FB. We could then conclude that DF is the perpendicular bisector. So see, it says, given the following congruent segments, DF must be a perpendicular bisector. So then you could say, oh, okay, well, these are all right angles, and these 2 segments are congruent. So that's that there. Most of what we're going to do, they look more like this. Although I just realized my letters got cut off here. Okay, so it's supposed to be DC. So this is supposed to be C, and this is supposed to be A and B, I think. Yeah. Okay, so it says DC is a perpendicular bisector. So them telling us this is mostly what you're going to do in this section. We need to know, okay, if it's a perpendicular bisector, I'm going to mark that these are right angles and that these are congruent automatically. And now let's proceed and look at everything else. It says find X in the measure of angle BPC. So it says AC is 5X minus 3. CB is 3X plus 17. Angle B is 43 degrees. So let's focus first on finding X. We were told AC and CB. Since this is a perpendicular bisector, these are equal. So you're just going to set them equal to each other. So you're going to have 5X minus 3 equals 3X plus 17. So we're going to add 3, subtract 3X. So that's 2X equals 20, X is 10. And again, I set them equal to each other because we were told it was a perpendicular bisector, making these pieces equal. Now it says find the measure of BPC. BPC is this angle here. We were given that this was 43. So these three angles make a triangle, right? So if this one's 90, these two have to add to 90. So if that's 43, this one's going to be 47. So the measure of angle BPC equals 47 degrees. So sometimes with a perpendicular bisector problem, it's about the angles, and sometimes it's about the segments. So you just have to know that 90-degree angle, they add to 180, and then these two pieces are equal. So that's the first one, perpendicular bisector. Do we have questions so far? No? Okay, there's 3 more segments that we're going to talk about. Next one we've already done before is an angle bisector. So we should know already that an angle bisector is something, by something I mean a line, ray, or segment that divides an angle of a triangle into 2 congruent angles. And so the reason why this is special is because now we're doing angle bisectors in triangles. So the directions here say create the angle bisectors of triangle triangle CAB. So when you have a triangle, each angle can be bisected and then they all intersect at one point. So I'll show you that. So I'm going to do all 3 angle bisectors in this one. So to make an angle bisector, if anyone does happen to have a protractor, or you can just watch, we're going to do this next week. You have to measure the angle. I'm going to do angle A first. So again, I'm going to put this right on angle A. This line here lines up with AB. So it should be set up like this. This is how we set up a protractor. Since I'm on the right-hand side of the protractor, see how like the protractor has 2 sets of numbers? There's a 0 on this side, and then there's a 0 on this side. So whatever side of the protractor you're set up on, because like if I was going to do angle B, I would set it up on that side. So you can do either side. Since I'm set up on the right, I'm going to use the 0 on the right. So find 0 on the right-hand side. So that means I'm going to use the inside numbers. So we should see that this is a 40-degree angle. Half of 40 is 20. So then you just make a mark where 20 is. And now I'm just going to connect this. When you do the angle bisectors, they always have to connect from a vertex to a side opposite. So you don't have to like extend it through the triangle. As I make them, I'm going to mark which angles are congruent. So because this is an angle bisector, this was 40 degrees, remember? So I just made these 2 angles congruent. So I'm going to put a mark here and a mark here to show that those 2 are equal. Okay, now I'm going to do angle B. So angle B, if you guys could see, I lined it up. This, I can't really, to make it super accurate, you're going to want to extend it, but you can kind of see if I extended this line here, it would go to about 65. So half of 65 is about 32.5. So that's going to be like here. And so I can mark this one congruent to this one. Okay, now to do C, I'm going to turn my paper. Oh, you can't see what I'm doing. Sorry. Okay, so it looks like C, again, I'm on the right-hand side now, so I'm gonna use the inside numbers. C looks like it's just about 75. So half of 70 is 35, so like 37 and a half roughly. So like around here. Which lines up exactly with those. So see how they all intersect at one point. Next time we're gonna learn about these points. They're called points of concurrency, but that's what it looks like. So every triangle can have 3 angle bisectors, 1 for each angle. Just like perpendicular bisectors, there are 2 theorems that go with this. So it says if a point, the first theorem, angle bisector theorem, if a point is on the bisector of an angle, it is equidistant from the sides of the angle. So that would mean, like, say for example, this point here is equidistant to the sides. So these are the sides of the angle. So these 2 segments would be congruent. So like looking down here, since CP is an angle bisector, which I can tell from these markings here, this would be congruent to this. Now, one thing I should mention, notice that they marked these right angles. And so the reason why you can do that is the distance between a point in a line, or a point in a ray in this case, is always going to be the shortest distance, which is a perpendicular piece. Like if I just said, like, what's the distance between P and ray CA? Like you wouldn't just draw in a random, like, oh, this represents the distance. It has to be the shortest path from the point to the segment or the ray or whatever, which is a perpendicular segment. So like what I mean is if I had a point in the line and I said, like, draw in the distance between the point and the line, you can't, like, you could draw it anywhere, right? But the actual distance is a perpendicular piece like that. So that will come up more next week, but I just figured I'd show you that. Okay, so anyway, so when you have an angle bisector, any point on the angle bisector is equidistant to the sides. Then you have the converse, which is the opposite. So if you had a point that is in the interior of an angle, which P is on the interior of angle ACB, and it's equidistant to the sides of the angle, which this one is, then you could conclude that it's on the angle bisector. So since AP is congruent to PB, ray CP is an angle bisector. This example is more like the ones you're going to do for your practice today. So it says MR is the angle bisector of angle NMP. So that would make angle 1 congruent to angle 2. Then they give us an expression for angle 1 and angle 2. So what do we do with them? We set them equal to each other because they're equal. Okay, so to solve, I'm going to bring over the 5x and add 16. So 24 equals 3x, so x is 8. Remember, if they also wanted us to find angle 1 or angle 2, you would take 8 and plug it in. Okay, so that's an angle bisector. Cuts an angle in half. The next one is called a median. So now we're getting into 2 that you probably don't know what they are, although median, usually kids associate the word median with middle, which is perfect. So if you thought of middle as soon as I said median, a median connects a vertex to the midpoint of the opposite side. So it cuts it in half. So if you want to think median, middle, midpoint, medians only give you midpoints of sides. That's all it does. It doesn't do anything with the angles. So we're going to create the medians of RST. And so what we're going to do is we're just going to measure each side and cut it in half and then connect it to the vertex of the opposite side. So if I wanted to draw in the median of RT, I'm going to first measure RT, which is about 6.3 centimeters. So that would be 3 and then like 1.5 millimeters. So 3 like here. And then I'm just going to connect this to S. So that's a median. This is congruent to this. Anytime you're like, not really constructing, but drawing in medians or whatever, make sure you're always labeling as you go. like labeling what's congruent. Okay, now we're going to do our S. So let's see, RS. It's like 3.6. So half of 3 is 1.5, and then half of 6 is 3. So it's gonna be like 1.8. Right here. We'll connect that to T. So then this is equal to this. So there's 2 of my medians drawn in, and now I'm going to do ST. So I'm going to measure ST. It's like exactly 6. So half of that is 3. So right there, I'm going to connect this. See how it's all lining up, and they all intersected at one point. That's how it's supposed to be. If you're following along with me and yours are not intersecting at one point, you just maybe measured incorrectly. But so that's what it looks like. Those are all the medians. So a median, if you're given a median, it just cuts it in half. So there's no theorems that go with a median. So we're just going to do a straight up algebraic example. So it says if CD is a median, so if we were told CD is a median, you need to know to mark that these are equal. This is a section, this is a unit where making note cards is really helpful. Remember at the beginning of the year, I was like, hey, make a little box of index cards. And every time we have vocab words, I don't know if anyone has been doing that, but this is a unit where it's very helpful to do that. So especially since like our quiz is going to be in school next week. So you can't use notes when you're in school. So it's really important that you know these terms like inside and out. And I just always remember, I've taught geometry now for a really long time. So I just always remember every year, like, especially in honors, like this is the section where kids get all of the theorems confused, because now next time when we do the points of concurrency, there's even 4 more vocab words. And so it's really helpful to make note cards. So like you have to know them inside and out. Median, mark the congruent segments. So you might want to make some note cards and just study them. Anyway, so it says the AD, so this part here is 1 plus 28x. And then AB, the whole thing, so it's important to really pay attention to what you're given, is 59x minus 1. So for this one, we're not going to just simply set them equal to each other. We were given a small piece and the big piece. So if these are equal, if this is 1 plus 28x, so is this piece, right? So then we're going to set up this plus this equals 59x minus 1. You can also do this, like 2 times 1 plus 28x equals 59x plus 1. I mean minus 1. So make sure that when you're doing your practice that you're paying attention to which parts you're given. So I'm going to distribute this. So it's going to be 2 plus 56x equals 59x minus 1. Let's add 1, subtract 56x. So it's going to be 3 equals 3x, so x is 1. It also says find the measure of dB. So dB is this one, so we're just going to plug in 1. So it's going to be 1 plus 28 times 1. So whoops, 1 plus 28 is 29. So that's the measure of dB. Okay, so a median we set equal to each, well, we don't set equal to each other always. Just know that a median gives us congruent pieces. Okay, so the last one is an altitude. An altitude is a segment that connects a vertex of a triangle to the side opposite that vertex, and it's perpendicular to that side. So basically it gives you, an altitude gives you a 90-degree angle. One way you can kind of remember it is if you think about what an altitude is like in real life, like if you guys have ever been on a plane and at some point when you're flying, the pilot usually comes on and is like, oh, we're at a cruising altitude of blah, blah, blah feet, whatever. Think about the airplane. The altitude is just like how high you are straight down, right, at a 90-degree angle. It wouldn't be like, oh, here's my airplane, my altitude is this like random like diagonal line. It's always like straight down to the ground, like how high you are. It's like the height. So an altitude is always a 90-degree angle. So that could be a way to remember it. So altitudes look different in a triangle depending on what type of triangle you have. when you have an acute triangle, you can draw in all three altitudes like this, and they're all inside the triangle like that. If you had a right triangle, and so the reason why is because an altitude has to go from the vertex to the side opposite the vertex. So vertex, side opposite, vertex, side opposite. So in an acute triangle, they're all nice on the inside. This is most of the ones we're going to do look like this. If you have a right triangle, here's a vertex to the side opposite. So there's one altitude. These other two bold pieces are actually considered to be altitudes. So because if you think about, I need to go from this vertex to this side, the only way to do it is to use this side of the triangle, if that makes sense. So this is one altitude, this is second altitude, this would be the third altitude. So this would be the altitude connecting this vertex to this side, would be this altitude here. So in a right triangle, you have one altitude that's inside and the other two are part of the triangle. An obtuse triangle is even weirder. So like this is the triangle we're looking at. From this vertex to this side, from this vertex to this side, you can make it down like there's one altitude. But if you think about from this vertex, if I try to make an altitude from this vertex to this side, I can't really, like there's no way for me to connect this vertex to this small segment here in a 90-degree angle. The only way to do it is if I extend this side and make it here, which this is not really a right angle, but I should have adjusted that picture. So it would probably be more like this. That would be a right angle. Get that. But you get the idea. So it would be on the outside of the triangle. This doesn't really come up that much, to be honest, but I just, sometimes you do see it. So sorry for my inaccurate picture. So this would be another altitude. 1, 2, 3. Really what you need to know about altitudes is just that it makes a right angle. So this is like the problems that you're going to do. It says AD is an altitude. This is D in case you can't see it. This is A. So anytime you're given an altitude, you're just going to mark that we have right angles. Then it says find X if ADC is this angle here, is 5X plus 10. So what do we know about this angle here? That it's 90 degrees. So you're just going to do 5X plus 10 equals 90 and then solve for X. So subtract 10. So 5X equals 80. X is 16. So that's really, I mean, altitudes are actually pretty easy, to be honest. I know that maybe this part was a little confusing, but don't really worry about that if that didn't make any sense. I just wanted to show you like how altitudes can appear in a triangle, different types of triangles. So that's what an altitude is. It's 90 degrees, nothing else about the segments. If you're given an altitude, all you can conclude is that you have a 90-degree angle. That's it. So, that's all the segments. So that's it for notes. Just to quickly recap though, I'm going to recap on this whiteboard real fast. So the 4 segments we have are a median, median gives you 2 congruent segments. That's it. Altitude. Altitude gives you 2 90-degree angles. A perpendicular bisector is kind of like a combination of a median and an altitude. It gives you 2 congruent segments and 90-degree angles. And then an angle bisector just gives you 2 congruent angles. So that's like a summary. That's the gist of what we just did. Does anyone have any questions about anything? No? Okay. So I've picked specific numbers for you to do. So you don't have to do all of the problems on here. Where's my sticky note where I wrote them down? Well, it's on Classroom. So, yeah, I don't know where my sticky note is, but if you go back to our Classroom post, this is your practice. Oh, here it is. This is your practice. So I want you to do 1 through 4. 1 through 4, it just has markings on the picture and you just have to identify what it is. Name the special segment. So is it a median? Is it an altitude? Is it perpendicular bisector? Is it an angle bisector? There's one of each. So you're doing 1 through 4, and then I picked 6, 7, 8. So 6, 7, 8, 10, 12, 10, 12, and then 15 through 17. So these should be super quick. And then I think there's 8 of them after that. So you can get working on this. There are a couple of them that have quadratics. So remember that when you have a quadratic, I think they're pretty easy to solve though. So when you have a quadratic, you can bring everything to one side and factor. There may be one of them though, that it's like x squared equals say 49. I don't know. Something like that you could solve by square root method. So I think you'll notice when you get there, but yeah, so that's that. Get started. Oh, I can probably stop recording.